Evaluation framework and methods. For the evaluation method of nursing facility locations, PostgreSQL var. 9.6.1 and ArcGIS Pro var. 2.0 of Environmental Systems Research Institute, ESRI, were used. The evaluation framework and process are as mentioned below. The distribution maps of the aging population and nursing facilities as well as a road network map are created in digital map form using GIS. These three types of digital maps are superimposed, and the closest road node from a representative point from each nursing facility and area, divided by town and street, is set on the road network map. The specialization coefficient of the population aging rate is calculated using the aging population in addition to the total population data from each area, and the results are added to the road network map. By applying the data obtained in section 3.1.2 to an algorithm, which is explained in the following section, the shortest route between each nursing facility and each area is calculated. Using the distribution maps of the aging population obtained in section 3.1.1 and the shortest route calculated in section 3.1.3, the evaluation points are calculated for each area. The age group being evaluated in the present study is those over the age of 75. There are many cases where those over 65 can use nursing facilities. However, according to Hashimoto, 2015, the life expectancy and health span in Japan have become higher in recent year, with the latter being 71.19 for men and 74.21 for women. Therefore, assuming most users of nursing facilities are over 75, the age group was set for those over 75. As for the evaluation target area, in order to calculate evaluation points according to each area, GIS is used to display the distribution of the aging population on the digital map. GIS is used to display the distribution of nursing facilities on the digital map. While nursing facilities include facility types such as admission type, commuter type, and other related facilities, the present study will only consider admission type of nursing facilities. As for the distance between nursing facilities and each area in the present study, the road network distance is used instead of the linear distance. This is because the linear distance may be extremely short compared to the distance when traveling along the roads to the nursing facilities, and this may cause the estimate of the travel distance of users to be shorter than it actually is. First, GIS is used to display the road network map of the evaluation target area in digital map form. Next, the node closest to every nursing facility and the representative point in each area will be set up on the digital map. The representative point is the central point of the area, and the nodes are the intersections and endpoints of the roads. This is set up as the distance is calculated according to each node. In the present study, the node set as the representative point of the area is the start node, and the node set as the nursing facility is the end node. In the present study, the distance is weighted so that the road distance of areas with a large demand is longer, while the road distance of areas with a small demand is shorter, as shown in the weighting pattern diagram in. If a user from a certain area selects a nursing facility that requires him or her to go through a transit area with a large demand, there is a high chance that there will be competition among users, as those from the transit area will most likely select the same nursing facility. Therefore, the weighting is conducted as mentioned above with the assumption that psychological distance of the users will be longer. Weighting pattern diagram. The specialization coefficient of the population aging rate is used as the weighting coefficient. The specialization coefficient of the population aging rate is the value indicating how high the population aging rate is in a certain area. Besides the specialization coefficient of the population aging rate, the population aging rate and the aging population can both be considered as a weighting coefficient. However, because the population aging rate is the ratio with the value always being 1 or less, the distance is always calculated to be shorter. Additionally, the difference in the aging population among the different areas is substantial enough to greatly affect the distance. On the other hand, the specialization coefficient of the population aging rate does not make the value too big or too small, hence, it is suitable as a weighting coefficient. The specialization coefficient of the population aging rate in each area is calculated. In order to calculate the specialization coefficient, the population aging rate must be calculated first. The population aging rate and the specialization coefficient of the population aging rate are, respectively, calculated using eq. 1 and 2, who. where A is the population aging rate of area percent, P75 is the population of those over 75 in area people, and pi is the total population of area people. Where SCI is the specialization coefficient of the population aging rate in area, A is the population aging rate of area percent, AI is the population aging rate of all areas, percent. The specialization coefficient of the population aging rate calculated in, 2, is added to the road network map using PostgreSQL. This is done by multiplying the distance between nodes by the specialization coefficient of the population aging rate. As a rule for addition, the specialization coefficient of the population aging rate is added if the nodes are in the same area as in nodes, I, and, 2, of. However, if the nodes are in different areas as in nodes, 2, and, 3, the average value of the specialization coefficient of the population aging rate is added. Example of specialization coefficient of the population aging rate added to the road network map. The shortest route between each nursing facility and each area will be calculated using an algorithm. A representative search method for finding the shortest route is the Dijkstra method, Dijkstra, 1959. However, in the present study, the latitude and longitude are used for the coordinates of the representative points in each area as well as the nursing facilities, and the estimate value of the shortest routes between the 2 points are available in advance. Therefore, an algorithm, which is the improved version of the Dijkstra method that can effectively calculate the shortest routes, is used. In general, when considering the shortest route which starts at the start node, goes through node N, and ends at the end node, the route is expressed as shown in 3. Where f niche the shortest route distance, m, g niche the shortest distance from the start node to n, m, on niche the shortest distance from n to the end node, m. Though f n can be easily obtained if the values of g n and h n are already known, in reality, the values of g n and h n are impossible to obtain beforehand. Therefore, the method of replacing f n with the estimated fn is called an algorithm, and it is expressed as shown in 4. Where f is the estimate value of the shortest route, n is the estimate value of the shortest route from the start node to n is the estimate value of the shortest route from n to the end node. An example of actually searching for the shortest route using an algorithm on a computer is shown in. In this example, the shortest route from coordinates 2, 2, 2, 5, 5 is obtained. The gray cells are set as impassable, while f, g, and h correspond to fn, gn, and hn of 4. However, g is the actual travel distance from 2, 2 to the current cell, and the distance for moving one cell over in any direction is counted as 1. Additionally, for the estimate value of the shortest distance from the current cell to 5, 5, h is set as the higher value of the difference between the x-coordinate and the y-coordinate of the 2 points. Example of shortest route calculation using an algorithm. The algorithm process is as follows. Calculate the values of f, g, and h, surrounding the first cell. Move to the cell with the value of f being the lowest. Calculate the values of f, g, and h, surrounding the move cell. Among the cells newly calculated in the algorithm process 3, if the value of f is the same as or lower than that of the current cell, it is moved to that cell. If the value of f is higher than that of the current cell, the search on this route is discontinued. Then, among the value of cells already calculated, if the values of f, g, and h can be calculated and the value of f is the same or almost the same as that of the current cell, it is moved to this cell. The algorithm processes 3 and 4 are repeated until the destination cell is reached. Calculate the values of f, g, and h, surrounding the first cell. Move to the cell with the value of f being the lowest. Calculate the values of f, g, and h, surrounding the move cell. Among the cells newly calculated in the algorithm process 3, if the value of f is the same as or lower than that of the current cell, it is moved to that cell. If the value of f is higher than that of the current cell, the search on this route is discontinued. Then, among the value of cells already calculated, if the values of f, g, and h can be calculated and the value of f is the same or almost the same as that of the current cell, It is moved to this cell. The algorithm processes 3 and 4 are repeated until the destination cell is reached.